Alrighty, I'm just going to show you a few examples of using conservation of energy in order to work some problems. Now remember, when we're dealing with energy, we can have total energy, which includes every possible form or type in a situation. Or we could be looking at mechanical energy, which are the forms of energy that are really readily available and easy to access to do work. Now when we're dealing with the idea of total energy is always conserved, meaning you always have as much as you start with as we do at the end. Mechanical energy, however, is conserved with a caveat, provided we have no friction. And even then, if you have things like sound and stuff, that's a whole nother story. But, as you saw in some lab examples, where I tossed a ball into the air and had it come down, or had a nice, pretty massive spring oscillate back and forth, we had really good conservation of mechanical energy. So in many situations, even though, yes, there is some friction, we can use conservation of mechanical energy to get some really good predictions going about motion of objects. Now, the nice thing about energy, of course, is if we think about the three forms of mechanical energy we've been looking at: kinetic, gravitational potential, and elastic potential, energy does not care who it is. So right now it might be kinetic. I'm a ball rolling across a flat floor. Do. However, the ball now starts to go up an incline. Well, now there's kinetic energy because he is in motion, but he's also gaining height. He's got some gravitational potential energy as well. So this energy that was all kinetic has now been distributed into two different types. When this ball gets as high as it can possibly go, i.e., we have, of course, the weight of the object, which is trying to accelerate it back down the hill, counteracting that positive velocity pushing it up the hill. When we finally have a velocity of 0, I have no more kinetic energy, it's gone. And all of the energy is gravitational potential. In lab, if we think about the idea of the ball being thrown and falling back, at the throw, all of the energy was kinetic. This is the point, the 0 height, from which we measured the rise. So this height, when we looked at problems working with a two-dimensional motion, that height was measured right from this level right here. Well, as my ball rises, we know it has a positive velocity but a negative acceleration due to gravity. On the rise, the speed is going to slow. That means as we go up, our kinetic energy is getting smaller and smaller and smaller because the velocity is getting smaller and smaller and smaller. But at the same time, I'm gaining height. So my potential energy, which starts small, or I should say really starts almost at 0 if I'm measuring from that point, is getting bigger as we climb, and bigger and bigger. At the very top of the rise, my velocity is 0. I have no kinetic. It's all potential. And as I fall back down, I see a reverse in trend. As I come back down, well, I start to lose gravitational potential energy. It's getting smaller and smaller because my height's getting lower and lower. And my kinetic energy, because as I'm falling, I'm speeding up, is growing and growing. Now, according to conservation of energy, this value of kinetic energy I started with to begin with, and I'll just clarify this, I'll just pull these off because some people are probably going to get confused. All my energy I started with is right there. Right here, that total is the same as that value. This total, the same as that value. That total, same as that value. In other words, as I'm rising, the same amount of energy is following me throughout the trip. I'm, however, donating it, kinetic over to potential, so potential increases, but at the expense of kinetic. Up here, this amount of energy is also equal to that value. So if this happened to be 100 joules, up here it's also 100 joules. And at every point in total in between. Coming down, I'm losing potential, but I'm gaining kinetic. And the sum at every point would be the same value as what I started with at the top of the rise, which is the same as what I started with at the very beginning. In other words, no matter where I take a measurement, the sum of all the energies is going to equal the same value. So how does that work in terms of the idea of problem solving? Well, energy, you can sometimes have one form or more forms at the same time. Let's say I have a bird that's carrying a little nut. The nut has a mass 0.06 kilograms. If it's given to you in grams, don't forget you have to convert. And the bird is flying at 2.1 meters per second at a height of 8 meters. Now, because the bird's carrying the nut, that is the speed of the nut. Because the bird's 8 meters above the ground, that's the height of the nut. So, don't think that the bird necessarily is doing something different than the nut. If that nut's in the bill of the bird, they're going at the same speed, they're at the same height. Bird drops the nut. When the nut hits the ground, I want to know the speed at which the nut hits the ground. Now you might say, well, I can use this with kinematics. I have a delta y, I've got an initial velocity. Yeah, but you know what? That initial velocity is horizontal. It's not vertical. And you might ask yourself, how do I deal with that? Is that like a horizontal projectile? Is it different than a horizontal projectile? I don't even remember projectiles. That's okay. With conservation of energy, we can work this problem just as easily. When my nut is being carried by the bird, it has kinetic energy because it is in motion relative to the ground, and it also has gravitational potential energy because it's at a height above the ground. That total amount of energy the nut possesses, just like the ball being thrown up and falling back down into your hand, will stay constant regardless of what the nut has been doing. So if I allow the nut to drop, as he falls, he'll lose gravitational potential energy, but he's going to gain kinetic. All his speed right now might be horizontal, but as he gains vertical speed, well, that just builds into his kinetic energy bank. When he hits the ground, which is where I measure my gravitational potential energy from, he'll have zero gravitational potential. All of his energy will be kinetic. So here's a situation where my object starts with 2 energy types and ends with 1. And I want to use that to find speed. Well, kinetic energy would be 1/2 mv squared, gravitational potential mgh, and kinetic energy 1/2 mv squared. Now we can assign those velocities little subscripts of initial and final. And I can go ahead and start putting in my information. 1/2, 0.06. I'm going to leave my units off just because this is going to get a little unwieldy here. 2.1 squared plus 0.06, acceleration due to gravity, height of 8 meters, is 1/2 0.06 v squared. And it looks like I'm going to have to write them down here. V squared. Boom, boom. And what do? Solve for v. There we have it. I don't have to worry about projectile motion or two-dimensional motion or anything like that. I'm done. I do have to remember, please take the square root of velocity at the end, but I'm done. Now some people might have looked at the formulas up here and said, you know, I've got a mass, 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 and it's all the same mass, 0.06, 0.06, 0.06. Can I do this? Yes, you can. I could have shortcut this particular process and done 1/2 initial velocity squared plus gh is 1/2 final velocity squared. And some problems will do that to you. They won't tell you the mass of the nut. They'll just tell you a bird's carrying a nut. Nut gets dropped. What's the speed of the nut when it hits the ground? I can do it because I don't need mass. The bird might have been carrying, it could have been a stork carrying a baby. It could have been a little bird carrying a nut. Ultimately, the stork or the bird traveling at that speed, at that height, the nut and the baby will hit the ground at the same speed. So if I'm dealing with problems that have kinetic energy and gravitational potential as my only two types involved, I can actually leave off mass because I really don't need it. So very common things we tend to see with these problems is something starting with all kinetic energy, such as a ball being thrown up into the air, water coming out of a geyser. How high is it going to rise? I could use some kinematics, or I could just say, well, I know the launch speed, and I want to solve for height. Done. Sometimes it's the other way. Something is at a height, and it gets dropped. All the energy starts as gravitational potential. It ends its kinetic, and I want to solve for the speed with which it hits the ground. GH equals 1/2 v squared. And I'm done. So problems with conservation of energy tend to be pretty quick and clean to work with. Now sometimes they'll try and trick you. Something's on an incline. Now we know these problems, they made us pull our hair out. Ball's at the top. I've got a length of a ramp. Go back to 40 meters from the last video and 20 degrees. And I want to know how fast is the ball going when it hits the ground, and your head starts to hurt. You go, oh no, I've got to break down the weight of the ball into components and oh blah blah and oh it's a big mess. Not with energy. Energy does not care you're on a ramp. In fact, it just makes it just loves the challenge. The only thing energy cares about is that you're a certain height above the ground. It doesn't matter how you got there, and it doesn't matter how you get back down to the bottom. From the last video, we said that height was 13.7 meters. We used the sine function with our 20 degrees and our hypotenuse of 40 meters to get that. G times 13.7 meters is 1/2 v squared, solve for v. That's it. You're done. You go, but it's on a ramp. It doesn't matter. Provided again that we don't have a lot of friction here. That v would be exactly the same whether the ball fell straight down 13.7 meters, rolled down my hill, and only accomplished 13.7 meters of actual vertical displacement, or whether we went around a whirly-girly slide like this. It wouldn't make any difference. Not at all. What height did I start with? What velocity would I end with? Energy doesn't care about your path. All it cares about is the value that I begin with and my value that I end with. Now, if you're working with elastic potential energy, you do have to stop and remember one thing. Unlike kinetic energy, which was 1/2 mv squared, and gravitational potential, which was mgh, elastic potential is 1/2 kx squared. Mass is not in there. So that nice little shortcut of, oh, GH is 1/2 v squared. No. You can't say GH is 1/2 kx squared, for example. Mass has to be there because you can't cancel it on this side. It doesn't exist over there. So that little shortcut does not work with problems involving elastic potential energy. You do have to include all the masses. So let's say you have a problem where you have a spring, and we're going to go ahead and give it an initial stretch from the relaxed length of 0.13 meters. The spring has a mass on it of 0.2 kilograms, and he possesses a spring constant of 12 Newton over meter. And I want to know what happens if that's my initial stretch. I go ahead and actually wind up compressing him to 0.08 meters. In other words, he was at 0.13, now he's at 0.08. So I stretched him out, and now I'm pushing him back in somewhat. Or I should say, I stretched him out, I let him go, and he's coming back up, and that's the point he's at right now. How fast is he going at that point? You go, what? How would you even know that? Well, that's where conservation of energy comes in handy. Right away, you might look and say, there's no way I could approach this with kinematics. I have no clue what to do. It's not a free fall situation, because this is not falling under the influence of nothing but gravity, because I got the spring trying to pull him back up. First blush, you might say I've got no tools in my toolbox, but you do. You have conservation of energy. I have a spring. He's right at this point right here, at 0.13 meters. I let him go. He's going to move in that direction, and as he does, he is going to speed up. What's the speed when he's at that point of 0.08? Well, that's where my energy will be able to work it out. At this location, all his energy is elastic potential. Why? I stretched him and held him. He's got no velocity. At this point, he does have elastic potential because he's still stretched out, but he also has kinetic energy because he's in motion. So, I go ahead and I set up a statement of conservation of energy where he has one form of energy to start, in this case elastic potential, and he has two forms of energy at the point where I'm going to take my measurement, elastic potential and kinetic. So my elastic potential is elastic potential, and I can call that guy initial and that guy final, plus Ke. If you hear snoring, it's my dogs. They're having a lot of time interrupting my videos today, but they're dogs. What can you expect? My elastic potential, 1/2 K, which is 12 Newton over meter. My stretch is 0.13 meters squared. Now that's not your relaxed length. That's actually a stretch that I put into the system. Final elastic potential energy, 1/2. Spring constant didn't change. And I'm going to put my 0.08 down here. Squared plus the kinetic energy of 1/2, 0.2 kilograms, and final velocity, don't have a clue, squared. Elastic potential energy to start, elastic potential energy as he moves upward at a certain point. He also has some kinetic energy, and again, I have to remember, don't forget to take the square root of the velocity at the very end. And you wind up getting 0.79 meter per second. So take each form of energy, ask yourself, what do I have to start with? What do I have to end with? It could be one type, two type, who knows? Write out the expression for each type, making sure you don't mess up initial and final conditions, initial final height, initial final stretch, initial final speed, and then solve for the one thing that you don't know. So conservation of energy is often a very quick way to solve problems for things such as speed and height when basic kinematics is going to be a little issue to work with. Alrighty, I will see everyone on Monday.